Hello. In the previous discussion, we learned about how an inverse filter can be used to restore a given degraded image. And we also saw that inverse filter doesn't handle any noise. And if at all we try to filter by using full filter, we could see that the output results was very bad. So in this class, let us try to discuss about how we can restore in the presence of noise also. Okay, so one of the way to handle noise is by using what is known as a minimum mean square error filter. It is also called as Wiener filter. Let us discuss this filter in detail. What we understood in the previous presentation is inverse filtering does not provide noise handling. So we saw this, how noise is going to affect filtering. So we will try to understand how minimum mean squared error filtering is used, which incorporates both blur and noise into the restoration process. What you see here is a one-dimensional representation of this filtering technique. So later we will consider a two-dimensional representation once we understand this concept. So what you see here is, suppose if I have a one-dimensional signal x of t, which is being captured by using an acquisition device, assuming that the acquisition device has got its impulse response as h of t, and assume that n of t is the noise that is getting added. So here y of t is actually the degraded data, degraded output. Okay, so and this y of t can be calculated by using equations which we will discuss in the next slide. So this degraded data, when it has to be in fact restored, what I need to do is I should pass it through a filter g of t. So this is the minimum mean squared error filter that we are going to discuss now. So when this type of filter is used, I'll get an output x hat of t, which is very close to x of t. So the objective of minimum mean squared error filter is to find and estimate x hat of the uncorrupted image, that means the clean image x, such that mean squared error is minimized, and this mean squared error can be represented by using this equation. We'll discuss this in detail in the next slide. And here E corresponds to the mean operation, and you know this is the error because x is the original, x hat is the estimated value, so the error, and the error is squared. And all of you have learned that a squaring error has an advantage, because if you do not have this square function here, there could be positive error and negative error which may cancel, and thereby it may mislead us saying that the error is less. So just to take care of the negative error, we usually square the error. That is why the name minimum mean squared error, MMSE. This is also called as Wiener filter. So MMSE filter is also called as Wiener filter. So let us try to understand some mathematics here. What you see here is the model that we wrote in the previous slide. Let us try to write the equations for the corresponding output. So we have made assumption that h of t is the impulse response. That means the system is LTI. So since it is LTI, I can write the expression for y of t as x of t convolved with h of t plus eta of t. So this is equation 1. Now x hat, the output of the filter, this is the filter I am using. Again, we are assuming that g of t is linear and time invariant. Therefore, x hat can be written as the corresponding input y of t convolved with g of t, where g of t is the impulse response of the Wiener filter. Okay, so this is the impulse response of Wiener filter or MMSE filter. Okay. Now, so how will we calculate the error? So if I represent error E of t, as I said, it is a mean squared error, and we have to minimize the mean squared error. So that means the mean operation is this expectation operation. The input signal is x of t in the time domain minus the restored signal is x hat of t. So the error in this should be minimized. This is what has to be done. Okay, but as you could see that these equations use convolution, so there is one convolution here and another convolution here. Just to take care of that convolution, we can even as well do the same thing in the frequency domain. That means I'll take the whole thing to the frequency domain, so you can write this as E of f in the frequency domain, expectation operation. So x of t becomes x of f minus x hat of f. We could do this because we have learned that energy gets conserved when you go from time domain to transform domain. So whether I minimize the error in the time domain or frequency domain, it's all the same. So this is exactly the equation what we have seen in the previous slide. Okay, so this equation is what I have written. Okay, so now we need to simplify these equations. So we need to now calculate E of f. So let us just substitute the values. X of f, I'll just write it as it is, minus x hat of f. X hat of f means I should take the Fourier transform of this equation. So if I take the Fourier transform, you know, y of t will become y of f, convolution becomes multiplication, and g of t becomes g of f. So this is equal to y of f into g of f whole square. So now y of f again can be written by using this equation, by taking this equation to the frequency domain. So I think we can easily write that. So this is equal to x of f minus y of f is x of f into h of f plus the frequency domain representation for n of t. We will use v of f and this notation is used because we are going to use n of f for something else later. So let us use v of f. So square. Okay, further simplification. I think there is one more term here. I'm sorry. With this, there is one more term g of f which we have forgotten. In fact, this is actually the frequency domain representation of v of f. Okay, so further simplification, we will get x of f minus, so let me just simplify this, x of f into h of f into g of f minus v of f into g of f square. This is modulus square. Okay, I will take x of f as common factor here, so you'll get 1 minus h of f into g of f all multiplied by x of f minus v of f into g of f. norm square. It means modulus square. So now we use a substitution. Maybe I think we can write this 1 minus h of f into g of f as say some r of f. This is only for making the equation simple. So let me just write it as 1 minus h of f into g of f. And what I want you to notice is um, h of f is actually the frequency domain representation of the degradation function, that is the filter, and g of f is the frequency domain representation of the Wiener filter. So h of f is actually the frequency domain of this, and g of f is the frequency domain of this. So since these are deterministic filters, this term r of f is actually a deterministic quantity. Okay. So now the expression by with this substitution is r of f into x of f minus v of f into g of f modulus square expectation of this. So all of us know that modulus square can be written as okay. For example, if you have something like um, modulus a square, this is same as a into a conjugate. So using this substitution, I can write the equation as, so it is r of f into x of f minus v of f into g of f, this term, into conjugate of this, r of f x of f minus v of f g of f, complex conjugate of this. So modulus is replaced by a into a conjugate. So with this substitution, now let us just try to simplify. We will multiply each term. So we will first take the conjugate on the second equation first. So we'll retain this as it is. This term is retained here. So conjugate I have to take. So it is r conjugate f x conjugate f minus v conjugate f and g conjugate f. So this is equal to, now multiply r of f into r conjugate of f into x of f, x conjugate of f, I can write it as x of f mod square. So I have multiplied these two terms. So the second term is minus r of f g star of f into x of f into v star of f. Then I'll take this term minus r star of f v of f g of f v of f x star of f plus minus into minus is plus, that is why. So it is v of f into v star of f x star of f into g star of f. So x star of f sorry, it is V of f into G of f, V star of f into G star of f. So this is G of f, G star of f into V of f into V star of f. You can write it as, in fact, it is actually written as V of f mod square. So we now apply this expectation operation. Remember, I have already told you that this term R of f is deterministic. So that means, so R of f is deterministic. That means you need to okay, take the expectation. So since this is a deterministic quantity, this is a deterministic quantity. When I take expectation operation inside, so what we get here now is R of f into R star of f into expectation of x of f square minus R of f G star of f into expectation of x of f V star of f minus R star of f G of f into expectation of V of f into x star of f plus G of f G star of f expectation of V of f square. So what you notice here is this term is deterministic. That is why it has come out of the expectation operation. And you know this term is deterministic. Even your G is also deterministic quantity because it's a filter transfer function. Similarly, R star and G, they are deterministic functions. Similarly, this. So they have come out of the expectation operator. Now, what you should notice here carefully is this actually gives you the expectation of two random data, that is x and v. X is your original image and v is the noise. Okay. Now, if you remember when I was discussing about the assumptions that we have made, what we assumed is noise is uncorrelated. Noise is uncorrelated with the input data or with image. So since noise is uncorrelated, this term expectation of x of f v, so because noise is also assumed to be zero mean, so this expectation operation is going to get cancelled out. So this will be the terms will be zero. So also this term will be zero. So with this modification, now our E of f will be R of f. So now I'll write the original expression for R of f. So it is 1 minus G of f into H of f into conjugate of the same thing, 1 minus G of f into H of f conjugate into expectation of x of f square plus G of f into G star of f into expectation of V of f square. Now these two quantities, this quantity is actually written as signal power spectrum S of f. This is denoted as signal power spectral density S of f, and this quantity is the noise power spectrum, power spectral density N of f. So that is why I use V of f in the previous case, so that N of f can be used for power spectral density. So here SF is the signal power spectral density, and NF is the noise power spectral density. Okay, so with this equation, let us now try to understand how we can minimize the error. So in fact, I have already explained these equations and we have written it. So I'll just go to the next slide. And this is what I told you. Noise is assumed to be uncorrelated, and assuming noise to be zero mean, obviously the expectation parameter value will be equal to 0. So SF is the uh, signal power spectral density, NF is the noise power spectral density, by using which we will get the expression. So this is what we derived in the previous slide. Okay, so now what needs to be done is, as I told you, minimum mean squared error means it minimizes the error. That means I have to minimize this particular equation E of f. Okay, that means I should find that particular filter such that the error is minimized. So the filter here is G of t, whose frequency domain representation is G of f. Therefore, I have to differentiate equation 8. I have to differentiate equation 8 to uh, equate it to 0, and the differentiation is with respect to G of f, because I want to find the value of G of f which satisfies this equation. So this is the output that I'll get. I insist all of you to just do this step, which I'm not going to show you. So if I differentiate equation 8 and equate it to 0, this is what you have to get. I think it's not very difficult to understand it, because when I differentiate with respect to G of f, so in this term, okay, I'm differentiating with respect to G of f, so these two terms will be uh, remaining. And in the next term, since I am differentiating with respect to G of f, this term continues to be there. And in this term, if I differentiate it with respect to 0, the differential of 1 is 0, minus differential of this function here with respect to G of f means I'll get H of f. So that is why you have that H of f and minus. I think you can verify this. It's not a very difficult derivation. So this is what I am going to get. And if you rearrange this, so in fact, again, you have to do some mathematical steps here, which I expect all of you to do it. So I'll equate this equation to 0 and then take the terms according to the requirement. And finally, what I want is G of f. So what is G of f? This is the filter transfer function. That means it is your MMSE filter transfer function or Wiener filter transfer function. So this is exactly the result. Okay, and this is in one dimension. Okay, so since it was a lengthy derivation, I took one dimension, but you can definitely extend it to two dimensions. So this is your two-dimension model. So the equations also, so instead of your okay, so your x of t will be your f of x comma y in two dimension, and h of t will be h of x comma y in 2 dimension, then eta of t will be eta of x comma y. Maybe g of t, we can write it as g of x comma y. So the corresponding frequency domain representations are written here. So h star of f here is replaced by h star of uv because 2 dimension. S of f here is replaced by sf of uv. Again h of f, n of f here is again replaced by s eta of uv because we wrote it as noise per spectral density. So sf is sf of uv, hf is hf of uv mod square. So what you get here is actually the transfer function of a Wiener filter in 2 dimension, which has taken both blur and noise into account while deriving. Okay, so some results are shown here. Before that, you can just slightly make a small change. What you can do is you can take this SF of UV to the denominator. So what happens is this term gets cancelled. Therefore, you will get back only H of UV. And here you will, in the denominator here, you will have a term K, which is equal to this. Okay, so another way of representing Wiener filter is by using this equation. So K is a constant here, which is the ratio of noise power spectral density divided by signal power spectral density. And normally we make noise to be white. So you know, white noise means the power spectral density is a constant. But the only problem now is we don't know the signal power spectral density. This is not known to us. Okay, so let us see some results. What you see is comparison of inverse filter and Wiener filtering. In the first case, this is actually by using inverse filtering, that to full filtering. That means the complete filter is applied, and in the next case, you are radially limiting it. This we have already discussed in the previous class, and this is Wiener filter, and obviously you can see that this is better than the other two. Okay, so this is exactly what we understand by Wiener filter. So some more results are given here. You can just have a look at these results also. So what you should notice here is the image is corrupted by motion blur and additive noise. That means this one. So the image is corrupted by motion blur and additive noise. And the second case, inverse filtering is done. In the third case, a result of Wiener filtering is done. And okay, for different cases, the results are shown. So I just want you to look at these results and observe that the result here is much, much better when compared to others. Okay, so that's about Wiener filter, and we'll now discuss about how a generalized Wiener filter can be written, and this is also called as a geometric mean filter. Just note down this equation, what it corresponds to. There are some new parameters alpha and beta introduced here. So alpha and beta, depending on different values of alpha and beta, this particular transfer function is going to act like either a Wiener filter or an inverse filter. So let us see each one of them. As I told, alpha and beta are positive and real constants. When alpha is equal to 1, filter reduces to inverse filter. Okay, so when this term is 1, then what happens is this term will be 1 minus 1, which will be equal to 0. So you will not have the second term. So what you have is this term. Okay, so you know that, let me just write it. So the numerator is h star of uv, and the denominator is magnitude of h of uv square, so I can just write it as h of uv into h star of uv, and these two cancels, so you are left with 1 by h of uv, and 1 by h of uv means it's an inverse filter. So when alpha is 0, that is the next case. So when alpha is 0, this term won't be there, because anything raised to the power of 0 is 1. This is equal to 1. And since alpha is 0, you can observe that, of course, you have a term beta. Anyway, this I can say it becomes a parametric Wiener filter where the parameter is beta. Okay, so you have this beta sitting here. Now, if alpha is 0 and if you make this beta equal to 1, obviously it becomes your standard Wiener filter. Okay, so when beta is made equal to 1, it is standard Wiener filter. Suppose if alpha is half, in fact, both the terms will be there, and it becomes product of these two quantities. That is the first quantity and the second quantity, and it works like a geometric mean. So that is why it is called geometric mean filter. And similarly, for different cases like beta is equal to 1 and alpha decreases below 1 by 2, then it tries to perform towards inverse filter. When alpha increases above 1 by 2, it turns to perform like a Wiener filter. That means you can just tweak the values of alpha with beta equal to 1 and make use of this filter as a general filter. Okay, so that is all to be discussed in this particular module, and I hope you have understood. I think there are a lot of equations that we have written in this particular lecture, but I think but probably it would be clear. Okay, so thank you very much for your participation in this lecture.